Okay, this is your 7.8. The name of the title is Using Exponential and Logarithmic Functions. So I'm just going to call it Applications because it's kind of how we actually use these out there in the real world. And what I'm going to tell you, you might not like, but as mathematicians, we've been very good this whole chapter learning about exponentials, and we've been, talking about percent growth for this exponential then, where b would equal 1 plus or minus the r, where the r is your percent of growth or decay, right? So I'll call it change. And we've been very good about that, and we've expanded it into compounding when we talk about money, and that led us to compound continuous. If you remember, a was equal to p e to the rt. And what we're going to do now is, the general gist of using exponentials and logarithms has really been overtaken by those natural logarithms. So this becomes the more standard way to write things using e or ln. So we're going to have new kind of standard exponential equation. Y is equal to a, using e as the base, so it doesn't have anything to do with the percent growth anymore, right? It's just a number that's fixed, 2.7 something. But so then what can change is up here in the exponent k x here, okay? So we could argue that e to the k is like b. Not necessary. This is what I want you to know right now, and this is what we're going to be doing for the rest of this chapter, is sort of using this formula for all exponential. And obviously, if k is positive, we're talking about growth, and if k is negative, then we're talking about decay, okay? I should also point out that the initial value for a doesn't change, right? So that's a is still your initial value. Let's be clear, not forget what this is. It is still the value of y when x is 0, right? So if you're starting your clock, your time at 0, then e to the k times 0 is still e to the 0, obviously, and anything to 0 power is 1. So y would equal 1. I'm sorry, let me say that one more time because I got it wrong. Y is equal to a when x is 0. So initial value is still a, like we always did it before. So one of my favorite applications is this carbon dating. And it's this idea that every living thing on our Earth is made, your body is made using carbon. And naturally occurring carbon has some small percentage that's in the form of carbon-14, which is radioactive. And so the carbon-14 is sort of decays, and you end up with the ratio, how much carbon-12 you have compared to how much carbon-14 you have, changes after a sample is alive. So once it's dead, all of a sudden there's nothing to regenerate carbon, and so the carbon-14 is going away while the carbon-12 stays. So you can use that ratio between carbon-14 to carbon-12 to sort of get the age of things, and that's how we do dinosaurs and other artifacts kind of stuff, particularly when we're talking about large time scales. So one thing we can do is we can ask ourselves, how old is something? If when you look at the sample of this artifact, you notice only 2% of what would have been expected, or the original carbon-14 is present, okay? So what you're going to do, and we're going to use the 2% is now present in the sample. So now present, the y is equal to 2%, 2 over 100, times the original a. Okay, so that's sort of interpreting 2% remains of the original. So let's use this as a substitution into the original equation, okay? So for y, we're going to use 0.02 as 2 over 100. A is equal to the original amount A. See what I've done here? I got the final amount equals the original amount times e to the negative 0.00012t, and I can cross out the a's, and I'm left with 0.02 equals e to the negative 0.00012t. And of course, here we are at this sort of exponential equation. I need to solve it by taking the log both sides. And of course, I choose to ln both sides. And when I do that, I don't know if I can fit it, but I'll try. I have the ln of 2, 0.02, I have a problem, equals, and here, right, the negative 0.0012t comes down in front of ln of e, but of course the ln of e is 1, so it goes away. And then I can just solve it for t. So t is equal to, what do I got? I got the ln 0.02 divided by negative 0.0012. And I could put that in my calculator. So I'm getting t is about, what did it say? 32,600 years. So we're not talking dinosaurs, maybe we're talking a mastodon or something. The other thing we can do is sort of write a model observing a population today, or maybe a population long ago and then a population today. So maybe we say something like, in 2007, I'm using an example out of the book, there was a population in a state of 9.36 million people. And then you look sometime earlier, so in 2000 we looked and the population had been earlier the 8.18 million people. And the question would be, write a model to describe this. And I guess we do this because, you know, we might expect it to have some predictive value. So maybe we could predict what's going to happen in the next 7 years, kind of thing. Being careful that, you know, the future what happened in the past isn't always going to continue to happen. But, you know, some people like to do this, and it sometimes works. So I'm going to start, because the model I choose to work with is this one that seems to be most prevalent, okay? And see what we start with here. So I'm going to use my initial value in millions is 8.18, okay? So that'll be at t equals 0. And so if that's t equals 0, then the 2007 is time equals 7. Okay, so I'm measuring time in years since 2000. Okay, and I'm measuring population in millions. So let's go ahead and write then the final population of 9.36 is equal to the initial population when I consider this time period, 818. E to the k is unknown, but the time has been 7 years. Again, I'm going to divide both sides by 8.18 because I want to make sure I've kind of isolated the exponential here. Grab a 1.144 or something is equal to e to the 7k. Now I'm going to keep that in my calculator so I don't have to round it. I just put that there to make the writing easier. But I need to ln both sides now, right? So I'm going to ln both sides. And I'll have to do that ln of this number, which is still in my calculator. I haven't rounded it there yet. But the 7k comes down in front of ln of e, and of course ln of e equals 1. So now I just need to solve it for k. K is equal to the ln 1.144 all over 7. Make sure you finish your logarithm before you divide by 7. So I'm going to take natural log of my second answer, close my parentheses, divide by 7, and I'm getting a value of 0.019, and of course I am going to have to round that to something reasonable, so that when I write my model, y equals initial value is still going to be the 818, e to the k was 0.01925. Darn, I ran out of room. I should have written that times t. Okay, here's where things get interesting, because we want to talk about radioactive decay. And the reason it gets interesting to us is the fact that there's a language for radioactive decay that involves half-lives, okay? So the half-life needs to be defined for us. The half-life is the time it takes for a sample to decay to half of its initial value. Time it takes to decay to half the original amount. Okay, that's called a half-life. It's used a Greek letter tau, okay? And if we were back in the old days where we were doing percent growth, this would be almost easier, right? The time it takes to decay to half, that percent decay is a 50% decay, right? And so we know what the percentage is, and we could use that, and everybody would be happy. I'm going to put it here, and I don't expect us to ever use it, though. I would say, in the old days, I would have said 1 minus the 50% raised to a t. So basically, it would have boiled down to a half to the t. So there's that, you know, it decays to half of its value. 1 minus 0.5 is 0.5, and I just decided to go back and call it a half. So you can see that 1/2 and why we call it a half-life. But of course, everybody writes it the other way. But we talk about it in half-life. So we got to go back and forth between these two ways of thinking about it. Okay, oops, I almost forgot one thing. We have to fix our time. Sorry. We want to reduce the sample in half every 1 half-life. So you're really asking to do the 1/2 thing, how many half-lives have passed? And to get into how many half-lives for the exponent, how many times I should times a half, you really need the t over tau. You got to get the tau in there somewhere, right? So that's where it belongs. And so what you're doing, you know, when the time is 2 tau, you would see the exponent becomes a 2, so you would be, you know, cutting it in half twice. So you really want to be counting up here, you really want to be counting how many half-lives, and that's why we have that t over tau. But I wouldn't worry too much about this formula. It's interesting. It's kind of one of a sort of a finer detail kind of situation. So this is the exercise we're going to do. I'll give you the half-life because it's a nice way to talk about something. The half-life of this particular made-up element for me is 5 years. Okay, so I know in 5 years I have half of what I started with. But how does that fit into the preferred model is to think about it this way. Let the time equal tau, which in our case is 5 years. Then you know your final sample is equal to half of your initial sample, okay? So we're going to put those two things into our preferred model. So let's take this and write it over here. Y becomes 1/2 A, and then I'm going to equal it to A. E is, remember, we know what E is. K is the unknown here, and T is the time it took me to get to half, which was the tau, 5 years. So take K times 5. So of course, what's really beautiful is the A's cancel. Now that the A's are canceled, I can take the log of both sides, and I choose log natural. So ln of 1/2 is equal to, remember that K times 5 comes down in front of ln of E. Remember the A's, this A is gone, right? And ln of E is 1. So 1 times 5K doesn't do anything. And I'll solve for K. K is equal to ln of 1/2. Then I'll take it and divide by 5. So let me do that. So I get my value of K from my calculator, and I'm really happy it came out to be a negative number because I was expecting this to be decay, right? So I need that negative exponent. So writing the model, y is equal to the initial e to the minus 0.1386 t. So that would be my model. And if I wanted to, I could, ask you for how much of the sample remains after, 20 years kind of thing. So maybe we'll do that next. So if this is our model, I could say my original sample consists of maybe, 9 grams. That's a lot. How much is left after, and let's say 20 years. Now, 20 years is a lot of half-lives, right? A half-life was only 5. 20 years is 4 half-lives. So, so we want to definitely have a smaller amount than what we started with by quite a bit. So that's just sort of an expectation. So I'm just going to say y is equal to 9e to the negative 0.1386, that constant we found, and 20 for the time. And I'll plug that in. And I found in my calculator 0.563 grams would be the amount left after 20 years. And that makes me feel good that several half-lives had gone by, and I do have quite a bit less. So great, we'll go over it in class. See you then.